Welcome to Investigating Quasar Data with Polars and Interactive Marimo Notebooks. My name is Christopher, and I will be your guide. This course is of the how-to variety and shows you how to create a dashboard in Marimo using astronomy data. Along the way, you'll learn about quasars, spectral lines, and measuring redshift, and, well, creating dashboards in Marimo. Our dashboard will include a Matplotlib graph, data cleaned and manipulated with polars, even more data fetched from the web using pandas, and interactive UI components that adjust the graph with switches and sliders in the notebook. If you're a space nerd, there is Quasar stuff here, so that's good. If you're a data science nerd, then even if you don't care about the space stuff, you'll see how to collect data from a couple of different sources and how to get it into a form that can be used. And, well, if you're a visualization nerd, then you'll love how powerful Marimo and Matplotlib are. From one nerd to another, whatever type you are, there's something here for you. Some of the libraries used to acquire space data can be a little finicky, so I've broken the course down into two sets of requirements. The primary focus is on the dashboard, and for that I tested with Python 3.13.5, Marimo 0.16, Matplotlib 3.10.6, and Polars 1.33.1. In the supporting materials dropdown below this video window, you'll find some CSV files that contain the data used in the dashboard. If you don't want to connect to the Astrolab database and fetch your own, you can stick with the provided CSVs. If you do want to follow along with the data retrieval side, I used pandas 2.3.2, LXML 6.0.2, and the Astro Data Lab client, Sparkle Client 1.2.6. For your convenience, the supporting materials download also has a directory named Requirements, which has two text files you can use to pip install these two sets of packages. Quasars are stellar objects that emit massive amounts of energy. They occur when black holes eat things, and the process of pulling the star towards the black hole causes all sorts of funky physics to happen. A celestial object's redshift indicates how far away it is. You find the amount of redshift by comparing known spectral lines to an object's emissions and calculating how much redshift is needed to match them up. Don't worry if that wasn't clear. The next lesson covers what you need to know. This course was built in conjunction with a colleague of mine who is an astronomy research assistant. One day, he demoed a tool his team uses to visualize and interpret all this data, and what you'll build here is a simplified version of that tool. The end goal is an interactive Marimo dashboard. Inside of that, you will graph quasar data, superimpose element spectral lines on top of it, then use a slider to change the amount of redshift applied to those lines in an attempt to match up the quasar's emissions. In case you're not familiar, here's a quick overview of the key tools that are used in this course. Marimo is a Python notebook. If you know Jupyter, Marimo provides similar capabilities, but I prefer Marimo over Jupyter as it stores the notebook data as a Python script, meaning you can use the same coding tools you're familiar with to manage it. Polars and pandas are both data frame libraries. These are in-memory representations of row and column data similar to a spreadsheet. You can do all sorts of slicing and dicing on your data in both of these tools. In this course, I'll use polars to reformat and clean some data, and pandas to acquire some data from the web. Matplotlib is probably the most common of the Python graphing libraries out there. It can be a little esoteric, but it's very, very powerful. To top it all off, Marimo speaks Matplotlib, so you can include graphs in your notebooks. Next up, I'll give you a bit of background on the science connected to the data you'll be playing with. In the previous lesson, I gave an overview of the course. In this lesson, I'll give you a quick introduction to the science behind the data you'll be interacting with. On your left here, you have our sun. Isn't it pretty? Don't look directly at it. It might hurt your eyes. Consider a sunbeam traveling to Earth. To give you a sense of the vastness of even our own solar system, at the speed of light, it still takes 8 minutes for that sunbeam to travel from the sun to you on Earth. If the sunbeam passes through a prism, it gets split up into its constituent colors. White light, like our sunbeam, is made up of many different wavelengths. When the light hits the glass, it refracts. That's a fancy word for bends, and the different wavelengths bend at different amounts. On the other side of the prism, you see the wavelengths separately because of this bending. Now, although space is mostly empty, the important part of that statement is mostly. Your sunbeam can interact with things along the way. In fact, a lot of those things it's interacting with are the atmosphere of the sun itself. Consider this lonely hydrogen atom. The electron in the atom is quantized. That means it can only exist at specific energy levels, which I've represented here by 3 rings. Hydrogen actually has more than 3 levels, but I'm trying to keep the diagram simple. When the sunlight hits the hydrogen atom, it energizes it, causing the electron to jump up 1 or more levels. Since the electrons are quantized, that jump absorbs a specific wavelength of light, which means that wavelength is missing from our spectrum on the other side of the prism. By examining the output spectrum, you can see which wavelengths got absorbed and know what level changes in what elements absorbed those wavelengths. By doing this, you can determine just what the sunbeam passed through on the way to your prism. In fact, this is how Sir Joseph Norman Lockyer discovered helium. The element helium is named after Helios, Greek for sun, and that's because Sir Lockyer was observing these spectral lines and discovered an element that wasn't yet known on Earth. Now, history is messy, and although Lockyer gets the credit, someone else saw the lines a few months before, but they thought the lines were sodium and didn't realize it was a new element. Also, Lockyer was working with a team, but let's stick with the simplified version of history and give Sir Joseph the credit. What goes up must come down, and the same goes for our excited electrons. After that sunbeam pushed it up a level or more, it eventually has to come back down. When it does, it emits the same wavelength as was absorbed. If you're looking at the blackness of space, you might see these wavelengths and know they came from an excited atom. Most of the time with stars, you look at absorption lines as you're looking at their light directly. With quasars, you might look at the absorption or you might look at their emissions. Quasars can be pointy and produce strong directional jets. If the jets happen to be pointed at Earth, you can look at the absorption lines. If the jet isn't pointed at Earth, it still excites the local atoms. When the levels of those atoms reset, their emissions can be pointed at Earth. Either way, you can see absorption and emission, but for the sake of this course, I'll be sticking with emission lines for our quasars. It isn't just hydrogen that behaves the way I described, it's all elements. Each element has its own absorption and emission patterns for each of the electron levels within it. And if that's not complex enough, ionization also has its own patterns. An ionized atom is one that's missing 1 or more electron. Space is a pretty harsh place, and quasars are where some really hardcore physics happen, sometimes stripping atoms of their electrons. A shorthand is used in astronomy to indicate an element and its ionized versions. For example, N1 means nitrogen with no ionization. It emits light with a wavelength of 653 nanometers. Astronomers often speak of these in angstroms instead, but that's an easy conversion as you just have to multiply by 10. N2 is nitrogen with 1 electron removed. See, if astronomers were programmers, they would have started counting at 0, and then the number would correspond to the number of missing electrons. But they aren't, and so you have the danger of an off by 1 error. N5, say it with me, is missing 4 electrons, and that emits light at a wavelength of 1,240 angstroms, or thereabouts. I did some rounding here. Because an atom has multiple electron levels, it can have multiple lines. The Balmer and Lyman sets are collections of hydrogen transitions. The Balmer set uses Greek letters, where H alpha is a specific hydrogen line. The Lyman series also uses Greek letters. Don't ask me what is in either of these sets or why you'd need both. That's past my level of understanding. Just know, for later on, when you see Ly in some Greek letters, that's a hydrogen line. Emission and absorption lines are measured experimentally, which means if you look them up in various tables, they might not agree with each other exactly. This has to do with precision and experimental error. For this course, I'm using the lines in a table on this web page. You'll see more on that later. I've got a bit more science to cover before I show you the dashboard, so this continues in the next lesson. In the previous lesson, I explained absorption and emission spectral lines. In this lesson, I'll be talking about redshift and quasars. Consider a thing that is emitting sound and moving relative to you. Its motion affects the frequency that you hear. If it's moving towards you, the pitch goes up, and if it's moving away from you, the pitch goes down. You can experience this by listening to the siren of a fire engine going by you on the street. This funky little animation, borrowed from Wikipedia, demonstrates how the sound waves get affected. As the car moves towards you, the sound waves get compressed, making their frequency go up. As the car moves away from you, the sound waves get elongated, making the pitch go down. This is known as the Doppler effect, or Doppler shifting. Doppler discovered this phenomenon by observing sound waves, but the effect happens with all waves, including light. If a celestial object is moving away from you, its wavelengths shift. This shifting of light is commonly known as redshift because the wavelength moves towards the red end of the visual spectrum. The change in question can be the object moving away from us due to its motion, moving away from us due to the expansion of the universe, and gravity can also have this effect, but let's not open the whole general relativity can of worms. Here on the screen, I'm showing the emissions of a quasar as they are observed on Earth. There's a line at 490 nanometers, another at 760 nanometers, and one more at 850 nanometers. For reference, that little rainbow on top is the visual spectrum, so the 850 nanometer line isn't something you'd be able to see with your own eyes. Modern telescopes can observe outside the visual spectrum as well, though. Quasars generally are moving away from us because quasars tend to be very old. This means they were earlier on in the formation of the universe, which means the expansion of the universe is dragging them away from Earth, so their emissions get Doppler shifted. The new set of lines on the screen are spectral lines for magnesium, missing 2 electrons, and 2 of the hydrogen lines from the Balmer set. There is a bit of trial and error in selecting the right lines and matching them to a quasar's emissions, but take my word that these 3 elements are in this quasar. Knowing that, you can determine how much shift happened. Redshift is calculated by 1 plus the amount of shift times the wavelength. A redshift of 0.752 causes the diagram above to transform into the diagram below. Finding the right emission lines can be tricky, but once you have them, you can find a quasar's redshift. The value here translates into about 7 billion light years. A quick aside before getting into quasars specifically. Astronomers use an angular coordinate system to specify direction. It has 2 terms, right ascension, that's the degrees around the Earth, and declination, which is the angle you're looking up or down at. This is kind of like longitude and latitude on a map, but in 3-dimensional space. If you're observing something in space, you have to normalize your position, and of course the Earth is moving, which just complicates things, but right ascension and declination are standardized, so the value in a star catalog is the same for everyone. You just then need to translate it if you want to point your telescope at it. In the first lesson, I gave a quick definition of a quasar, but let's drill down a bit. Quasars are luminous, active galactic nuclei. Their name comes from the original term quasi-stellar objects. Observers figured out that they weren't quite stars, they were something else. And that something else is a hungry black hole. The galactic nucleus part is because quasars are typically from the really big black holes found at the center of galaxies. And if you've ever heard of a blazar, that's the same thing, but the jet is pointing in a different direction. The jet caused by the black hole eating things produces a mind-numbingly large amount of energy. In fact, it can be several thousand times the emissions of the Milky Way. Quasars are by far the most energetic things in the universe. Several million quasars have been identified, with about 1 million fully cataloged, including their spectrums. The closest one to Earth is 600 million light-years away, while the furthest is over 13 billion light-years away, near the dawn of the universe. The picture on the right here is an artist's rendition, but it gives you a bit of a sense as to what's going on. This is the graph of the emissions of a quasar. In fact, it's the one I used to demonstrate redshift. The 3 peaks in the graph correspond to the emission lines of magnesium-3 and the gamma and beta values of hydrogen in the Balmer series. The spectral lines have been shifted, which is how the redshift got calculated. A couple things to note. The wavelengths here are in angstroms, and the amount of energy, which is the height of the graph, is known as flux. Also, real-world data is messy. There's a lot of squiggly going on here, and a big part of what astronomers do is taking multiple measurements and teasing out the data. If you ignore the noise in the 400 nanometer range, although it is messy, there are several distinct peaks in the flux. The three I've highlighted are those for our spectral lines. You may vaguely recall that this is a Python course. Our goal is to use Marimo to visualize spectral data like this, then create movable overlays of elemental spectral lines whose position changes based on a redshift slider. You've been patient as I've science geeked out. Next up, I'll show you how to graph a quasar's spectrum using Matplotlib and Marimo. In the previous lesson, I explained redshift and introduced you to the massive stellar objects known as quasars. In this lesson, I'll show you how to take a quasar's spectral data and graph it in a Marimo notebook. You've spent 2 lessons on science stuff, so how about a quick reminder on our goal? The intent is to create a dashboard where you can interactively overlay spectral lines and change their redshift to match a quasar's data. The data I'm using comes from the Astro Data Lab, which can be found here. The Astro Data Lab has several different databases. The one I'm interested in is known as Sparkle and has its own Python client for accessing the data. To build the dashboard, you'll need to find a quasar to visualize, fetch its corresponding spectral data. Once you've got that, create a Marimo notebook to graph the data, and you'll also need spectral line data. You take that, overlay it on the graph, and once all that's done, you'll add the interactive parts to the notebook, allowing you to adjust the redshift values for the spectral lines. All of that is a lot. It'll take us several lessons to get there. This lesson focuses on graphing the spectral data. As such, I'm going to use a CSV file with the data in it rather than fetching it from scratch. The CSV in question is called fluxdata.csv and is available in the supporting materials dropdown. I'll use Polars to read the CSV file and then Matplotlib to graph it. All of this will go in a Marimo notebook for visualization. In the overview lesson, I told you what libraries are needed for this course. For this lesson, you'll need to pip install Matplotlib, Marimo, and Polars. As always, you should use a virtual environment for package installation. For ease of reading, on the screen here I've split the bash command up into multiple lines. If you're typing it all on one line, you won't need the backslashes. Those are the bash shell's continuation character. Now, off to the Python REPL for a quick intro to Polars in case you haven't used it before. Polars is a data frame library, which means it is kind of like a spreadsheet with rows and columns. In case you need a review on how it works, let me show you the code you'll need in the dashboard. You start by importing it. Convention is to alias the import as PL, similar to how PD is used for pandas and NP for NumPy. Data science folks like their abbreviations. The read CSV call reads data from a CSV file into a data frame. The resulting data frame, that's DF for short, see, I told you, abbreviations, contains our quasar's spectrum. Let's look at the data. When you evaluate a data frame in the REPL, Polars shows you a bit of information. The shape is the size of it. Our data frame has 7,781 rows and 2 columns. The first column is named wavelength and the second flux. The F64 is short for 64-bit float, which is Python's floating point number. The summary here shows the first 5 and the last 5 rows of our data. You can reference a single column through square bracket operators. The graphing call that I'll be using in a minute expects 2 columns rather than a single data frame, so this kind of notation is how I'll pass the columns to Matplotlib. Speaking of which, this is some Matplotlib code. This is the exact code I'll be putting in the Marimo dashboard, but I put it in a file for now so that I could show it to you. To start with, I need Polars, and convention is to alias the graphing part of Matplotlib as PLT, short for plot. Yep, another abbreviation. Here, I'm reading the CSV file just like I showed you before in the REPL. And this is the start of the code that creates the graph. Matplotlib is a little weird. It just assumes you'll only create one graph, so you just start using PLT functions and it automatically creates a graphing object behind the scenes. I don't particularly like this approach, and there are other ways of doing it, but this is the most common way, so I'm sticking with convention. This first call specifies the creation of a figure to put the graph inside of. The tuples specify the size. My American friends will be happy to know this size is in inches, although it doesn't really matter as Marimo will resize it to the browser's width. This call sets the title of the graph. This long, ugly value is the ID of the quasar in the Sparkle database. I think I'll take a page out of the data science book and shorten the name a little bit. I'm going to call it Serena. This sets the x-axis label. The paired dollar signs tell Matplotlib to use LaTeX math format. The /A is the sign for angstroms. This is the y-axis label. The units of flux are rather messy, and this is another LaTeX math value. The x and y lim calls specify the data boundaries of the graph. And finally, this is where the actual graphing of Serena happens. The plot call creates a line graph. It takes two arguments, the set of x values and the set of y values. I'm getting those from the individual columns from the polars data frame. If you're running this file as a script, the show method will launch a viewer so you can see your graph. Inside of Marimo, this bit won't be necessary. Alright, now you've seen the code, let's create a Marimo notebook and paste this into it. When you pip installed Marimo, you got the Marimo command with it. You use this command to create and edit notebooks. Let's do that now, creating one called dashboard.py. Two quick things. First, note the name of our dashboard is a Python file. This is one of the reasons I prefer Marimo to other notebook tools. The data file is a valid Python program. This solves a lot of the problems found in other tools where they use something like JSON, and that can be problematic to merge with other files. The Marimo edit command starts a web server and shows you its URL here. That URL is where you interact with the notebook. See the headless argument? Well, you might want to leave that out. With it, you have to copy the URL manually into a browser. Without it, Marimo will launch your default browser with this URL for you. As I do a lot of web dev, I tend to have several browsers open at a time, so I use headless mode so I can make sure I open it in the browser of my choosing. Speaking of which, let me go launch that browser. Here I am in my browser. Let me paste that URL. And this is the notebook. Most things require the Marimo module imported, and the first cell here shows that as default. So let me accept that and run the cell by pushing the play button. Notebook cells can be Python or Markdown. Let's start with a title. So I'm going to use a Markdown cell. Click the Markdown button. And there you go, a pretty title. Now I'll add a Python cell. And inside here, I'm going to paste the graphing code I showed you earlier. Click the play button. Takes it a second. And there you go, you've got a graph. If you're coding along with me, feel free to play around in here a bit. Make some edits to the graph. For example, change the boundaries or the titles. Remember, once you've made a change, you need to hit the play button again to refresh the output. Walk around a little, get comfortable with it. You're going to be playing with this dashboard for the rest of this course. The next two lessons are about how I got to the CSV file you just graphed. Let me show you how to look things up in space.